think there's some mic. That's from you. Okay. I think I'm pretty sure you'll not regret being here. I'm pretty sure you'll enjoy this very much. I enjoy every talk Stefano gives. So let me introduce to you Stefano Stramigioli. We need actually about, I think, at least 45 minutes just to finish the introduction. But okay, so I'll keep it very quick. So Stefano Stramigioli, he's the head of the Robotics and Mechatronics lab at the University of Twente. He's an a lot of things on the top, just you know, the cherry on the cake. Okay, so he's an IEEE Fellow, and he's also a member of the Royal Holland Society of Science and Humanities. From 2018 until 2023, he has been an ERC laureate. So yeah, I got an ERC Advanced Grant, and this is actually the results of this project that he'll tell you about. So I hope Stefano also shows you some of the great work they also do at the Robotics and Mechatronics group. So Stefano can talk for hours. So what you see here is only, you know, a point in a big sea. I hope you enjoy this talk. So the floor is yours, Stefano.
Thank you very much. So first of all, thanks a lot to everybody. It's a pleasure to be here. It's my first time in Saudi Arabia, and I was very positively impressed about many things. So it's great to be here. And I very much appreciated that how respectful people go with each other. So it's congratulations for that. So I'm happy to be here also because Rami was a student of mine and actually my best student ever, I think, together with another guy, two best students ever. And he's been working on the project I will talk about. So I've been giving, this is my second lecture, and I will give another one tomorrow. So yesterday I did something more mathematical. So I tried to kind of split things. But in case you have questions, please interrupt me anytime. And I have a lot of slides. I can switch if you have, if there's been a board. If you have a question, I can do and address whatever you want to list to hear. So I have the pleasure and honor to chair this lab, which I built it up basically in the year. It's a robotics and mechatronics lab, and I mean the philosophy which is behind is I think that we want to innovate, to do new things. And I like very much this citation of Peter Drucker that says the best way to predict the future is to create it. And I think that in order to do innovations, you need two things. You need intelligence and you need creativity. And creativity is something like an art in some sense. And intelligence is more something you learn because of study. And I study every single day. And I hope I will have many years before I die to keep on studying, because that's the things I actually like the most. And I think that another thing which is very dear to me is synergy. I think academics, institutions should be a place to collaborate, to synergize with other people. And in fact, I very much, I try to build the lab exactly in that way, where people can work with each other. So the lab is a big lab. We have about I think 60 people, and with a running budget of about 5-6 million euros a year. And it's all, by the way, most of it is external acquired funding, because we are not as lucky as you guys, as faculties present here, that you get PhD students for free from the university. It's actually I would move here, but. So, and we work on different things. So from modeling and other things, as you see, these are the feeding technologies that we work on. And a lot of application is in healthcare. We'll talk about it tomorrow, a bit more details. And in that respect, it was pleasure to have been collaborating with MOMEN for many years. Inspection and maintenance is something that got a lot of attention in the past. Now is kind of fading away. But also I've been working a lot in inspection and maintenance for oil and gas in the previous years, and then a lot of future application. And now actually I'm doing theoretical physics most of the time. I do whatever is interesting to be done. I don't. I think that science should be a place to create, as I said, to synergize. So whatever is interesting, I work on it. So this is just a glimpse of some of the activities of the lab. So it's really from very fundamental theoretical work to very practical work. And some things are domain independence, like, software architectures that you can apply to any kind of robot, so to speak, Or if you go, for example, specifically to the medical domain, you need a lot of knowledge in the domain itself, or in the previous, as I said, in inspection and maintenance, you should know about ATEX regulation for explosion and all these kind of things. And this is a glimpse. So these are some of the things I will talk about, mostly what is here. And tomorrow I will show some of the actuation technology which we developed, which is MRI technology, which is basically, we have a patent, we have a company now with 35 people working in London. And I cannot say a lot about that company, but we'll actually hear, I'm sure, in the coming year. So more about the talk now. Robots are, are physical systems, and energy is the mathematical embodiment of the invariance of a lot of physical laws. I'll come to that later. Physical interaction of robots with humans or the world is the core of a lot of robotics application, and mathematics is the powerful tool the engineer at their disposal. But nevertheless, far too often, in my opinion, engineering is done without looking at physics and not doing the mathematics precisely. And I think that is, as an engineer, I've been trained as an engineer. I think what I do now, I'm more a mathematician and theoretical physicist. But I think that, my heart is in engineering. The way to look at the nature, to look at things in the engineering way, you can do much better than the physicists can do, in my opinion. But the precision that is learned in physics and in mathematics, I think that's a good combination. That's my opinion. So I want to give you an idea of 4 base concepts, which is something that has been driving my interest in the backline in all my time. And actually, as a matter of fact, when I moved to the Netherlands, I'm Italian originally, and I moved to the Netherlands in '92. Some of the young fellows here were not even born, probably. I was confronted with these things that were called bond graphs, and I really didn't get the point. And one day clicked, and from that moment on, I cannot see nature without this kind of concepts. And the advantage of looking at like this is cannot be overestimated. These are some of the things that I've been doing in these settings. These are some of the books and the papers that I've been published. But it's always been driven by this sport-based thinking, and I'm very happy that Rami is here, because now he can share it with you, because he's been also infected by this virus by me, and he's a phenomenal scientist that I strongly encourage to talk with him about these things also when I'm left, and of course I'm here. I want to play a game with you, ladies and gentlemen, and about a paradigm shift. Do you know what this is? This is called a dovetail. Okay, these are 2 pieces that mechanically can be inserted. In a lot of assembly, this is used. Okay, so it basically fixes 5 degrees of freedom and leaves 1 degree of freedom free. All right. So this is basically you can shift it and it will slide in this way. Okay. Now, can these 2 blocks move? Who's for yes? Please raise your hand. Who's for no? Please raise your hand. Well, it can move. What's going on here? What's going on here? You see, sometimes we look at things and we do not think hard enough. And we just from the surface, we draw conclusion. This is, by the way, not only a problem in science, but in society in general, by the way. Okay, but that's a more philosophical story. But I think it's, you see now that you need to think further than what you see. Okay. And the question is, beside the symmetry diagonal, are there other ways this can move? What do you think? And now you start getting the point, right? Now you are critical, right? You're thinking. So you see, of course, there is, there are actually an infinite number of things. All those motions which keep invariant what you see in the front are possible, basically, because you don't see what's behind, right? So there are a lot of these motions. Okay, and I'll skip. There are many that I could show you. But the bottom line of this discussion is that is very important in science is to break out of the box. To think about what is your preconception that you have, and sometimes just to think crazy, it really can help. So what I want to try to give you some idea of this port-based thinking during this lecture, and I hope you will appreciate some of the idea and will be triggered to look into it a bit more deeply. The very standard way to do a lot of work, like for example in computer vision, okay, is what is called the pipeline way. So you have basically that you say you have a part and interacting another part, the part interacting another part, or you process software-wise some things in a certain way. That's not the way the nature works. Okay, and nature works very differently. Nature works like this. Whatever you do, you always have a feedback. And so if I shake the hands to somebody, it's not that I force the position of the force. It's just the way, the dynamics interacts between these two things, all right? And this is deep because this is not just shaking hands. This is everything in nature. I actually am working on in quantum theory, okay? Also these things, the collapse of the wave function. I don't know if you have any feedback, and you know anything about quantum physics, but there are a lot of things that physicists just use and is conceptually actually wrong, the wrong way of doing it. Okay? And Newton told us, because action reaction is basically one of the fundamental things in nature. Okay, and I will tell you more about this in this context of these birds. I like philosophy also, and Aristotle says in all things of nature there is something of the marvelous. It's unbelievable if you look at certain things in nature, how beautiful the world is. And being Italian, I cannot avoid to talk about Leonardo. Leonardo da Vinci, that I hope you have heard about it, is more than 500 years ago. He was actually, fascinated by the beauty of birds, okay? And he started to study birds. Of course, he didn't have the mathematics that we have now. And in this context, I also have got in contact with, these guys? Have you ever seen these guys? Okay.
It's a
the Mythbusters. Okay, so Jamie is a very good friend of mine. Actually, I gave them the honor degree of the university as divulgator of science because a lot of attraction of young people for technology has been inspired by them. And especially Jamie. Jamie's very nice. Jamie's a very nice guy. And he's very deep, by the way. And with him, we looked at also, we tried to work on something with the Mythbusters to try to fly a person. But Discovery Channel at that time was more like in explosion. It's cheaper to make explosion, more easier to make explosion than to do some good science. So it didn't work out eventually. But if you look at science, if you look at nature, if you look at a picture like this, it's just you could watch it for quite a long time. So what we've done in Twente, so in Twente we have this bird. It's a robotic bird, which is actually like a falcon. It weighs like a falcon. It has more or less the same frequency, flapping frequency as a falcon. It goes up to 80 kilometers an hour in 5-4 winds. There are a lot of toys and things that fly around, but there is no other toy that I know in the world. This is not a toy that can fly at that speed in that wind condition. So this is really unique. So just to give you a glimpse, so you can see on the left, this is the way the bird flies. If you see it, you cannot distinguish it from a real bird. This is now in slow motion. And you see also the deformation of the wing. So that actually is fundamental to have the deformation of the wing. And we got a lot of attention with this thing, the number of award recognition. We take the Tech Transfer Award. We got the Best Paper Award, the cover on the Robotics and Automation magazine, etc. And so it's a very, very nice device. But the question is, of course, why does it work? How does it work? And by some computational fluid dynamics include the kind of conclusion, the hypothesis, I should say, is that if you have a plane which is a fixed wing, you don't like turbulence, right? You want to have a laminar flow, and this laminar flow creates a different impression that gives you lift. That's basically it. And every time that you have a separation of flow from the wing, that's a bad thing, okay? And then you start shaking a little bit. But actually, birds do nothing else than that. So they basically move the wings in a way that generate these vortices and this shedding, what is called a reverse von Karman sheet. And you see here, it creates a jet. And that's how the propulsion of a flapping bird actually come around. And it turns out that there is a, the Strouhal number is a number that actually is unitless. And that gives it's a way to characterize this situation in a way or another. And all animals that either fly or swim actually have a Strouhal number which is between 0.2 and 0.4. So there is this something in these relations. But that's as far as people have an idea about it. But the question is why and how does it really work? Okay. And only understanding can make you systematically give you insight in make it even better than what it is. Okay. I like very much, Wittgenstein. He was an Austrian philosopher and mathematician. And he said, what we cannot speak about clearly, we must pass over in silence. And there are a lot of politicians nowadays that actually have never heard about Wittgenstein. But anyway, I think that if you want to understand how flapping flight actually works, you would like to understand much better how to do it. And I believe, reason to believe, and I was confirming these beliefs, that port-based thinking was the way to go. And I was very, very fortunate to set up a fantastic team. You recognize some people there, okay? And so here is our friend here, Rami, and it was phenomenal. For me, this project was just a gift from heaven, because I rediscovered, I was very busy. I'm a big group and a lot of management things, and during this project, I realized that what I want to do until I die, and I hope to live long enough, is to do science. Okay, and this was the first step on this. So I'm very, very fortunate that I got this project and that I had to work with people like Rami and other people that I really enjoyed, not only from scientific but a personal point of view. Aristotle said, the Greek divided knowledge, epistemology, which is a part of philosophy, in two parts. Techne and episteme. Techne is basically more like related to engineering, to constructions. And episteme is really the conceptual thinking, how you more the mathematical way of thinking. And in the history of philosophy, there have been other examples that do this. And so in the project, I wanted to actually look at both things. What is the good part of technics, of the engineering, and what is a good part of real science that is behind it? And I will first talk about the more conceptual thing. I talked about pretty deeply about mathematics yesterday. If you have questions, I can do it online, no problem. Please do not hesitate to stop me on that anytime. So if you have the bird, you can decompose. One thing is that, engineers are much better than physicists, for example, is really to decompose problems. René Descartes, one of the philosophers, was, cogito ergo sum. You may have heard this sentence, I think and therefore I exist. Is because he really was one of the first to say, if you want to understand something, you need to decompose it. Human beings are not able to perceive more than 6 to 9 things at the same time. So when you do mathematics, you try to collect symbols, and in this way, because that really helps you to think. So if we decompose, and this is what Port can give you, it can give you a systematic way of how to decompose physical parts and then to recompose them together. And in fact, I'm working with a very good friend and excellent mathematician and theoretical physicist, which is Friedrich Schüller, that Rami knows very well, who has, the best course in differential geometry you can find on internet. He was really puzzled because we met by chance once in Germany, and then he moved to Twente and we were working together because he was puzzled about this way of thinking. So it is deep. So, and if you have this, you have, the rigid body. That rigid bodies are reasonably simple to describe. And if you want to know everything about it, you follow Rami's course. And then you can interconnect with the wing. But then things get nasty. Because if you have a wing, the wing is deflexible. So you are talking about nonlinear elasticity. Okay, it's not a rigid thing. Because we actually found out in the bird that if the wings were rigid, it wouldn't fly. So it's not a 2D problem. It's really a 3D problem. So the shed of these vortices are not just 2D. They shed on the tips of the wings. And then you have the fluid around it. And, the fluid around it is described by Navier-Stokes equations, which are nonlinear PDEs, which are, pretty nasty, okay? And not only you want to connect these two PDEs, because you want to connect the elasticity of the wing to the fluid around it. And we found out that we needed to develop new mathematics somehow in a different way to describe about this port. And it turns out that the clue for all this was what are called tensor value differential forms, which open our minds. Then I started thinking more on this, and then I'll mention maybe later something. I realized that, quantum physics and gravity can be unified by that. And I had very nice, because I've been working 2.5 years on this paper, which is only 60 pages, but I could have written easily 300 pages of math on that. And it was my first editorial rejection ever. Physicists just don't get it, okay? So I will have to dissect it pieces by pieces and feed it but I think really that this is the way to do it. I'm convinced. I hope I will be able to see that people see it before I die. Let's see. Because story of Boltzmann, Boltzmann's statistical mechanics, you may have heard about it. That he developed statistical mechanics, and then people said this guy's nuts, okay? So basically, at a certain point, he killed himself. And then after was that, this guy was right. I'm not going to kill myself. Okay, so the core of the Portwings project was to study the physics of the robotic birds in a decomposable manner, okay? And to do it in a completely free geometric manner. Because I think, we should not be fooled by coordinates. I think that, I was as an engineer, this was not stressed enough. I have realized by hitting my head against the wall in these things that covariant thinking is really very, very important, because sometimes we make decisions which are very much connected to the coordinates we choose. And that's not physics. It's just a result of our imagination, okay? So in Portwings, this is Descartes, René Descartes. We did a lot of things. So the first things we tackled was actually to model the opaline fluid in Euler equations. And that was the first publication. You can recognize the first author, and the last author is me, but the first author is this guy. And actually was very nice, because when Rami arrived with Federico at that time, I didn't want to see any publication for at least a year. It's not that I didn't want to, because I said you would need to study now for a year this differential geometry, believing you invest, the publication came out, and then after the publication was just like, phew. We published one thing after the other, top journals, as you will see. So this was the first thing. The second thing was how do you study advection? Like, for example, fluid can transport things like entropy, or certain compressions can't be transported. So we kind of really look at the mathematics that to describe continua, basically, in a reasonably restricted context. So this brought to the second part of this, which are very long article, by the way, and then we went to the full Fourier-Navier-Stokes equations. And then we published a couple of papers on physics of fluids, this journal number 1 on fluids. And also we look at Fourier-Navier-Stokes, so also how the entropy actually develops in these things. And a lot of the things that still need a lot of attention actually have been developed there. Then the question was, one of the biggest questions was, all right, now we know how to describe the fluid. But when the wing moves in the fluid, you have two PDEs. One PDE, which is the fluid around it, right? One PDE, which is nonlinear elasticity of the wing. But it's even nastier than that, because these two PDEs are interacting with each other through the boundary of the wing. But not only, this boundary geometrically moves and deforms. I mean, you cannot think about anything nastier than that, but we nailed it, because in this paper, we showed how to do this kind of thing. So if you have two PDEs that actually have a boundary that deforms, we have developed the math in order to do that. And then we had basically sorted out everything about fluids in a continuous setting. But of course, if you want to do some engineering, some learning, some control, you want to discretize stuff. You want to have numbers, okay? You want to program in the computer. And then this was actually a crucial point in the project, because we realized that we had learned half of the story without looking at the numerics. And looking at the numerics, a lot of things came out that we were blown away. Okay, and in fact, these are the things that also now with this physics stuff I'm working on plays a big important roles. But we have found a way to do numerics in a way which is what is called structure preserve. And I will say a few things later on in my talk. And then we went to the elasticity, and this was actually really a phenomenal work that Rami did. He led the writing of these papers, of these two papers. And as long as I'm concerned, these three papers, I think I mentioned later, are basically characterizing nonlinear elasticity in the best way that I've ever seen. Okay, and of course there are genius of science like Jerry Marsden from Caltech that have been working on these things for a while. But he, for example, he did something that it was hiding stuff, and we had actually a discussion about these things many times. Okay. So what is this port-based thinking? So first of all, a bit of history. This guy was Harry Painter. Harry Painter was professor at MIT, and unfortunately, we knew, of course, I knew him, but he also knew what I was working in that early times in screw theory. And he wanted to meet me, but I didn't have the pleasure to meet him because at a certain point he died. But he was the person who really had the vision to put this port-based thinking in the world, so to speak. And then these two colleagues and great friends, Bernard Maschke and Arja van der Schaft, started and say, okay, this bond grass business is very cool, but there is much more onto it. We need some more fundamental, some more mathematics that describe this properly. And they developed all the theory on port Hamiltonian systems. And I was infected by this virus, then I passed then to Rami, and I started working these things. I never stopped. Okay, so port-based things is actually, after a lot of thinking on myself, is I have a certain vision on this. And I think the port-based things is all about symmetries and physical laws. Do you know who this lady is? Very good, Amy Noether. Einstein would have never, Einstein had a problem because he wanted to have energy conserved when he studied general relativity. And then Hilbert at that time and Noether was the lady that actually found out what was going on, realized that there was something strange in the symmetries of space-time. So to have an inverse invariance for any kind of diffeomorphism and blah, 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 she was the one who actually solved the problem. And in fact, all physics that we know nowadays is based on conservations. And when there is a symmetry, there is a conservation. And this is Amy Noether's work. And David Hilbert and Albert Einstein said that she was the most important woman in the history of mathematics at that time. What Noether's theorem says that if you have a symmetry, then there is a conserved quantity. That's basically the core of the theorem. And she knows for that in physics, but the old group theory is what she developed. So she did much more than what is actually known in physics. And what is energy? As an engineer, we use energy all the time. But she was the one who actually understood what energy is. In this history, I could give an history. I have slides about the history of thinking about energy. Clausius and Joule and all this was an experimental thing that people tried. But what it is came clear for this. Energy is nothing else than a thing that is conserved because physical laws are invariant in time. That's it. So you know that energy is not an absolute thing. It's what is called as a gauge value. So, for me, the kinetic energy of that laptop, for you, the kinetic energy of the laptop is 0, right? But for me, it's not 0 because it's moving backward, right? So you see, it's not absolute. It's dependent on the observer, okay? Instead, power is something which is absolute. And anyway, there is a lot to be said on this story. If you have a question, I will be more than pleased to tell you. And Albert Einstein says, the basically thing, he said, all laws of physics will be one day overthrown, but what will always stay is thermodynamics. And in fact, what I'm trying to develop in theory I mentioned before is precisely what comes out. Information theory and thermodynamics is everything. The rest is what comes behind it. Okay. And so the idea of using energy as a kind of Esperanto, as a lingua franca that everybody speaks, is an interesting thing. And this, of course, is known in physics because Hamiltonian theory is the base of classical physics, the base of quantum physics. Okay, but what Port-Hamiltonian system theory can give you is actually a Lego physics, because it has not only the idea of a generating function like an energy function that gives you the dynamics, but it also has a way to compose things via these ports in a way which is very, typical engineering way of thinking, okay? In network terms like Kirchhoff and Kirchhoff laws and kind of things. And, the theories, the structure, the mathematical structure are different, but for example, well, normally in Hamiltonian theory, you think top down, okay? Instead, in Port-Hamiltonian system theory, you develop the kernel, the atomic parts, and then you can build it up, okay, by interconnecting it by ports. Hamiltonian theory is closed. Port-Hamiltonian system theory is completely open. You can develop the, Port-Hamiltonian model of the wing, and then you have a Port-Hamiltonian model of the fluid around it. You click it. Okay, that's the idea. It's really open. So, and the model you do for the wing is independent of the kind of fluid you use, because if you put the wing in water, the other model would be the same, but the interaction is the way you describe it is the same. Dissipation, boundaries, and a lot of things. This is really a conceptually advanced way of doing things. Okay. So let me tell you how this works very, very roughly. Okay. If we have a physical system and we accept the fact that, due to the symmetry of physical laws, that we have this concept of energy, which is very useful, the question is, suppose I want to decompose this system in two parts, okay? How do I actually describe this interconnection? Okay? What is the proper way, mathematical structure that I need? Well, if I want to keep as a guiding principle the fact that energy is conserved, that means that if I split something, then the total energy I had is now partially one side and partially on the other side. And then I have the situation that if the energy goes down from one side, it will go up on the other side. So because the total energy should be conserved. Okay. Now, then something else, the action-reaction I told you before, comes into play, because you say, this symmetry, why should be one part of the system more important than the other part of the system, right? So there is the dual influence. It should be able to turn it around and have the same kind of reasoning. So we can say, okay, there is something, we don't know yet what it is, which I call E is something else that E, this guy basically set E for this guy. And so this is an output of this somehow, and it's an input for this, and the other way around for F. Okay. And then the question is, what is the nature of this E and F in order to be able to say something about it? And the interesting thing is that this power, as I said, power is invariant, right? I told you that energy is not. But power is. If I look at the power transfer between two systems, and you observe it, or I observe it, meanwhile I'm moving it, it's exactly the same. And power is a scalar, it's just a number. It's an invariant quantity, which is a scalar. And that will give the answer, because then it means that the structure, the nature tells us these two E and F should have, is basically, turns out, also Kirchhoff laws play into the game, that this should be a vector space, an element of a vector space. And this should be an element of what is called the dual of the vector space. What is the dual of a vector space? Is by definition, is the set of linear operator on the element of the vector space to a real number, which we call it power. So when you study mechanics of electricity, of electromagnetism, of fluid dynamics, let's take the mechanics example. People say that forces are vectors. They are not. Well, actually, they are vectors, but they are different vectors than velocities. If we call velocities vectors, forces are dual vectors. Because if you pair a velocity and a force, whatever dimension they have, you get the real number, which is called power, which is invariant. And you could show, I could show it very easily, that if you change coordinates, the way velocity change coordinates is different than the way that forces change coordinates. And unfortunately, also in my university, we don't teach it to our students because they say that every change of coordinates is orthonormal, and you don't see the difference. But if you go to polar coordinate, you see the difference. If you go to dimension, if you go to do robotics in the proper way, you see the difference. Okay, so it's very important. And I didn't even say whether these vector spaces are finite or infinite dimensional. In fact, they are not for the bird. They are infinite dimensional vector spaces, but nothing changes. So it turns out that you can write this with what is called the power bond. And this power bond characterizes two things at the same time. I even now got rid of the causality. You know, I'm not telling you who's giving what. I'm just telling you if this gives E, the other GUIs give F, but can be the other way around because this half arrow only indicates that if I pair these two things in the way I told you, I get a real number. If it is positive, means that that power goes in this way. If it's negative, it goes this way. So this arrow is not a causal arrow. It's a positive power energy arrow, okay? And it turns out that, you know, for electrical circuits, this vector space is real, is just a real number. So velocity and currents are just too real. It's easy. There's no geometry there. But if you go to multi-body dynamics, that turns out to be what are called the algebras. And in fact, it turns out that any physical system, if you want to decompose for reasons that are very subtle, and I actually want to write a tutorial on this because people do not see this, needs to be Lie algebras. Lie algebra and Lie groups is a part of mathematics about symmetries, everything that, you know, Noether described. And if you go to infinite dimensional systems, things get to this stuff which I said before, tensor value forms. And then the sky is the limit. You can do any kind of modeling that you ever think about. Okay. So just to give you, you know what this painting is? This is it's a painting that represents the academia. Okay, the academia of Plato in the Greek times. Okay, and this is Plato, and this is Aristotle. Okay, and you see that Plato indicates the heavens, so the mental, the cognitions, and Aristotle indicates the ground. Okay, the world. So this why is the issue of techne and so the technology and the rational way of thinking. And this sentence was actually written in the entrance of the first academia that Plato founded. Archaeogemetros midias isito means in Greece means let no ignorant of geometry enter, because for the Greek mythology, for the Greek at that time, geometry was a symbol of knowledge, a symbol of beauty. Okay, and I like this very much because I love geometry, and I think that indeed geometry should be a guiding principle for the science we do. And then you can show this just to give you a quick example. If you have an amplifier, for example, connected to a motor, okay, you have a voltage and you have a current. Okay, you see the symbol I gave you before. That's a port. That's the power that they exchange. If you have a motor, you go to a joint, then you have a torque. It becomes torque and angular velocity, for example. But then if you have two rigid bodies, then these ports become more complicated. These are this Lie algebra I was talking about. This would be what is called a twist, and this would be what is called a wrench. Okay, and due for action-reaction, you will have the same twist and the opposite wrench or the other way around. So these are the kind of things you do. And without, you could generalize this to infinite dimensional systems. And in order to do that, you need to be very careful. This is something I touched yesterday in the lecture I gave in mathematics. What we realized was that it's the huge difference. It's very important to split what is topology and what is geometry. I don't have the time to go into details, but I would be more than pleased to tell you more separately. And the idea is that, if you have a fluid and you have a wing and you have the boundary in between, okay, then you want to develop a mathematics that would work not only in this case. That was the goal. So it should work in all dimension, coordinate invariant, applicable to all physical domain, and possibly in curved spaces, because one of the things, for example, in space-time, you want to have curved spaces to handle gravity. And the only way to do it is exterior calculus. This was something that was not taught to me as a student, but I have realized that this is the way that really in my opinion, we should do integration. And I tell you why. This is a slide I showed yesterday as well. Vector calculus, which is the standard way everybody does, PDEs kind of stuff, was actually developed by, I missed Heaviside. There should be Heaviside in between. I've forgotten in these slides. I use an older slide. Because Maxwell, when he did the Maxwell equations, actually used the quaternion to do that. It was mathematically developed by Hamilton, and then was Heaviside. After that, it basically worked on these things and modified, with the variational gradient, rotation, and all the things that we now teach to our students. But then the point I want to make here is that, and then Riemann put integration, so Riemann integration that we learn, okay? But then a lot of other guys came in, Elie Cartan, de Raam, Grassmann, Poincaré, and we are still teaching vector calculus. Vector calculus is inferior, is worse, is not generic, etc., etc. And vector calculus was actually in the T-side relativity and magnetism from Maxwell is 152 years old. Okay, and we are teaching Riemann integration, which is 171 years old. And we know, physicists know that Riemann integration is bad. There's Lebesgue integration, because if you want to do through integral and infinities, that doesn't work, Riemann. Lebesgue is better. But exterior calculus is even better. Okay, and I'm completely blown away about how powerful this piece of mathematics actually is, and we discovered it, and I went even further on these things. I will skip this slide because I mentioned it, and then just to give you a glimpse, why is this so beautiful? Because once you have these things done to do the PDEs, you get a lot of insight to do discretization for free. Because if you do discretization, what you have, these are symbols that you don't know, but this is a field. It means, what a field is nothing else than something which has a value everywhere, okay? Vector field or tensor field of any kind, okay? And once you want to discretize, what do? We just take space, the field is defined upon, and we split it, okay, in pieces. So what we do is we divide it in blocks, we mesh the environment, we say, right? And then there is a process to basically associate to this mesh certain numbers, finite numbers that describe physics. So you lose information, right? But then you can parameterize with functions, partial finite elements, that's called finite elements. Then you basically associate functions to these values that you give. And then you can reconstruct the physical space, which is called the interpolation, okay? So basically what discretization is in this context is basically say, okay, this is a vector space, it's an infinite dimensional vector space. I can show you on the board infinite dimensional vector space, but you should think about it as an infinite dimensional vector space. And this orange subspace is a finite dimensional vector space within the infinite dimensional vector space, okay? So the physics is basically the field, the real field we want to model is this vector. Okay, and by means of these things, we project it on the space which is generated by the mesh we did. Okay, and this is basically the finite element reconstruction. So this is the error that we compute in these finite element ways. Okay, the magic of this stuff is that it turns out that this map, if this map is commutative with respect to an operator D, which is the D we use in differential calculus, which is an operator which is intrinsically baked in this exterior calculus, then if we have something like this, with what we have what is called topological preserving discretizations. And that means that we can actually do things much more precise than anything else. I am 100% sure that, if we would implement this in proper software, ANSYS would be out of business. Because if you do with this technology, we have examples that we take a mesh of 3 elements. It will be stable. It's just, it will give you the best with 3 elements, but it will be stable. That's not the way ANSYS works. If you work with these tools, sometimes if the mesh is too small, it gets unstable, you get funny things, okay? So it is really, really powerful. Okay, and there is a lot to be said that I will skip in for a matter of time. So let me conclude getting to This method is much better as a lot of things also to respect to time to simplicity integration. There is a lot to be said. I want to tell you a few things about the technical side. So what we did from experimental point of view, and then show you a video and close down. So the technical, so the more technological point of view, we've also been working how to manufacture, for example, the wings or certain sensor in the wings. So we've been working on also printing, for example, carbon doped material in the polymer, so that we could actually measure the deformation on the various things. And I bought a very expensive toy at that time. I have 230,000 euro bubble generators to just make a lot of bubbles to basically seed the flow. You will see the experiments. And thanks to that, we could actually grab a lot of 3D data, fluid dynamics. And this, of course, is not steady flow. Okay, this is unsteady flow. So it was a very complicated campaign that we did. So I'll show you now a video, which was a video that we worked very hard and to build and to coordinate. And Rami, what happened? Oh gosh. I forgot to, because I cannot. Oh, this is really annoying. Okay, well, maybe it's not too bad. I let me just put, if I can. Well, hopefully it will not be cold anymore. So let me show you the video.
Nature is amazing, and birds are amazing creatures, but we do not fully understand yet how they can fly. Could we really understand the magic of flapping flight so that we can build robots that can fly better than the robots that are currently available? The robird is the only robotic bird in the world which can fly in up to 5 Beaufort wind and at a speed of 80 kilometers an hour.
And can be autonomous. This is just here, but it can be autonomous.
It looks like it, but do we really understand the underlying physics? We believe that flapping flight is achieved with a combination of flapping and twisting of the wings, which creates detached vortices which generate thrust. But are we at the moment using the optimal combination of the oscillatory pitching and plunging motions of the wing? To answer this question, an experimental setup is built in the wind tunnel of the University of Twente to see how the wing moves and how the stream of air moves around the wing while it's flapping. This allows for exploring the optimal wing motion for the robird. A helium-filled soap bubble generator is installed, which blows thousands of bubbles per second into the wind tunnel. 4 high-speed cameras film the bubbles to capture the movement of air around the wing with the shedding of vortices. Furthermore, a force sensor at the root of the wing can measure the resulting forces on the wing, like lift and thrust, and reflective markers on the wing can be filmed with cameras to track the wing movement and deformation at a sub-millimeter scale. We've studied the flexibility of the wing since it's an important part of why the robird flies the way it does. Different than many people think, intelligence can also be embodied in the material and properties. A brain without a proper body is useless for locomotion. We want to bring this physical intelligence in the wings of a robotic bird, and in order to do so, we created smart wing designs and smart mechanisms which are able to change the mechanical stiffness of the wings to change the flying behavior. But how can we precisely describe the physics of a robotic bird with deformable wings interacting with the air around it? The unique feature of the approach we followed to describe dynamical physical systems is that it relies on energy and geometry. Energy is probably the most fundamental concept unifying the various branches of physics and explaining how nature works. In the Portwings project, we used the Port-Hamiltonian framework to get insight into the energetic fundamentals and transport phenomena of fluid dynamics, structural dynamics, and fluid structure interactions. In the Port-Hamiltonian framework, we describe any complex physical system as a network of energetic modules interconnected using power ports that characterize the energy flow within the system or exchanged with the environment. For example, if we consider the flapping wing setup we developed, We describe it as a network that represents the dynamics of the driving mechanism, the elastodynamics of the wing, and the aerodynamics of the air around it. The power supplied from the power source flows to the electric motor, and then some of it is stored as kinetic energy in the mechanism's inertia. Some of it is dissipated as heat and noise, and the rest goes to the flexible wing. The power supplied from the wind tunnel is also transferred to the wing through the moving boundary of the wing and the airflow injected inside the wind tunnel. In each cycle of the wing's flapping, the power supplied to the wing oscillates between kinetic energy and elastic potential energy, while the power that flows to the air is either stored as kinetic energy or dissipated in the vortices formed due to the wing's flapping motion. A Port Hamiltonian description of this physical system differs significantly from the standard approach of continuum mechanics using coordinate-based tensor calculus treatments. We rely instead on coordinate-free exterior calculus and describe the network structure of the system using so-called Stokes-Dirac structures. This methodology allows us to intrinsically handle open boundary conditions and thus use, reuse, and combine sub-models in such a way that a real Lego of physics would be possible. Consequently, this leads to the development of structure-preserving computational algorithms that allow us to efficiently and robustly simulate these physical systems to produce predictive computer models of the world around us. The real advancements in science and technology are only achieved with a deep understanding of the fundamental theory, as well as proper engineering and experimental skills targeted to the goal to be achieved.
I'm very happy and thankful to. So this is a video that was very expensive because it's professionally done, but I've seen it many times, of course, but I think it gives an idea of the whole picture, and you've recognized another guy there. The video. So it brings me to my conclusions. I think that really true knowledge comes with deep understanding of a topic and its inner working. And I think, especially for the students among the audience, value the time and the fortune you have about being a university, because there is nothing else as beautiful as learning about the world and the physics and everything that's been created. I think that port-based methods resulted really in substantial fundamental contributions about the work that we've been doing and floppy flights, but this was just a seed. I see it as a seed. For me, this was really a seed to see in even much deeper kind of research, okay? And we needed to develop new tools and because they were just not available in the literature. And I think that's the progress that I really like to be contributing to. Port-based thinking is really a different way of looking at things, and I invite you to be curious about it in the setting of these games I played with you guys. That you see, there is something behind that you may be worth having a look at because there's something to be offered. Okay, and then discretization methods which are there. There could be a lot of work done in this fact because I think really that. If there would be manpower to implement this theory in more executional things, we would have tools for engineers which would be much more precise and powerful than the one we actually already have. Okay, and as I said, now this brought me to develop a paper that is a preprint on the internet if you want to have a look at that. And that was the paper that was editorially rejected. The biggest paper and biggest contribution of my life was for the first time in my life editorially rejected. But I just need to chop it down. I have no doubt of the content that it contains. But and Rami is a way that it can help me to write things properly because he's a master in these kind of things. But I really think that this is the way nature works because duality, my discovery was that I don't know if you know anything about gravity of quantum field theory, but you know that these two theories have never been, people have tried 100 years to try to combine them. And I think the crucial point that people didn't see is that the geometry is actually created by the quantum fields, and the dual fields actually interact in a way. It's like the dual fields, like I give you a velocity and I give you momenta, and I tell you it's one thing. What can you tell me about the thing? The mass, right? Because the mass is that's the goal. That's the idea. It's as simple as that, but then to infinite dimensional space. So that's what I do. So this is for the students around you. My personal advice. I think that, you know, I would say once you work on something, once you model something, my learning that I realized is so important to choose the right mathematical structure. If you use Rn, as I was saying yesterday in my seminar, if you use Rn can be just a set, can be a Hilbert space, can have a lot of structure. Get rid of Rn. What is the structure you need for your problem? Choose it. You should have enough structure, but not too much, just enough to describe your problem. And that has to do with what Poincaré was saying, that the art of mathematics is to give the same name to different things. What is that you need to describe? Then let the mathematics guide you, because if you have a structure and you know that within that structure, those mathematical operations make sense, that means that those mathematical operations make sense for the problem that you describe with that structure. Okay? You can define angle. For example, you know, angle is what we use, but you can define angle between operators. And that has a lot of meaning. Okay. There is something in information geometry, for example, which is a name that I always forget, is an Indian name, which is very long. For me, it's very difficult to remember. That with this angle, you describe basically the distance between probability distribution of any kind of. They are beautiful stuff that just the mathematics can lead you with. Okay. Be critical on each step. So, you know, analyze properly. You know, is this true what I'm saying? Why is it be true, etc., etc. But also at the same time, something that, for example, I discussed with this good friends I mentioned before, Friedrich Schuller, is extremely precise. But I think he does, with what he can do, it should be also more following the feeling. You know, the creativity side of the story I was saying, you know, the intelligence and the creativity. Because I think that that is the way to do it. And I think that real knowledge, what is called epistemological growth, is not really about solving a problem, but it's really understanding why and how to solve it. Thank you very much for your attention.
Thanks a lot, Stefano, for the great talk. We don't have a lot of time for questions, but we will open the floor for very urgent questions. So
I'm here, so if you know, I have, unless you plan something for me, I have time to answer the question, whatever you. I'm sorry that I didn't realize, but I wanted to show you the video, and the video is a bit longer than I thought. Yeah.
But so we have some good news for the students. I think I'll ask the graduate council to actually announce that. So that's before we open the urgent questions.
Tomorrow, inshallah, we will have the pleasure of having Prof. Stefano to have an open discussion session organized by the graduate club. Mainly, some few questions will be prepared already. Then we'll open the discussion area to be like to get more knowledge and ask whatever for the students or anyone. Ask Prof. Stefano whatever like questions you can want to know more about and so on. Because of the time we have maybe today, so you will have more time tomorrow, inshallah. It's planned to be from 3:30 till 5 approximately. The venue will be like announced soon. We will send an email like after the session. We're like organizing the place for it. So inshallah, we're waiting for you tomorrow.
Okay, so in case you had an urgent question that you need more time, so now you have, okay, so you can settle down, maybe think about it a little bit more, and then you can ask it tomorrow. Inshallah, you'll have much more time for these students to interact and to get more guidance on the philosophical part, you know, as a researcher and as a scientist in general, and also on the technical stuff. So there was tons of technical stuff here that I'm pretty sure you maybe got interested and you need some more time to digest. So this is what the session is for. But now let's open the question for the urgent questions or people that don't plan to attend maybe tomorrow. Yeah.
So what are the technical problems faced in the experiment and how to overcome it?
In the experiment?
Yes.
Well, we're a lot because, you know, the flapping system that, for example, you have seen was the work of one person. So no, we have the team there. So for Ricardo worked on this, and it was really nasty because you wanted to basically flap that system at up to 4 or 5 hertz, okay, which is a big win. And at the same time, you wanted to measure, synchronize the force, okay, that you felt, and you want to measure the deformation. So in a non-stable and a fluid, of course, with this bubble. So this was nasty, and in fact, it was funny because the whole thing mechanically was designed, and then we tested it; it was working, and then we went inside the wind tunnel, and it was not working. And said why? And we were looking at the mechanics. There is something which is called electromagnetic compatibility. I don't know if anybody worked on this. Basically, we had to redesign the whole electronics because the switching of the motor was going so high that within the wind tunnel there were interference, electromagnetic interference, and we had to redesign the complete electronic part. We thought that was the last of the problem. Mechanically we need to be fast, and the sensor, and then we had to. And a colleague of mine, so I asked a colleague of mine who works for Thales, is an old IEEE Fellow in this kind of stuff, and look at this and says, no, that's not the way it should be done. So. And everybody has his knowledge. So and we redesigned it, and that was a big thing. And then we could do the campaign. But that was the biggest, and we lost a lot of time for that, unfortunately. Yeah. I don't know who's first.
So when you have like a collapsing mechanism which allows the wing to come inward while flapping downward.
No.
Second question.
Yes.
Does adding this enhance the report?
Okay, so the wings are not folding in. Okay, are fixed, but we have a system that actually can glide. So we have a mechanism that when it flaps, okay, it can flap and create thrust, but you can also stop the wing in a certain stable configuration, then you can glide. And that's easy. The more difficult thing is how can you transfer again to flapping, because there's a lot of force that you need to apply. So we basically have created an elastic compensation that when you release the wing with a certain locking mechanism, that you basically then accelerate and then start flapping again. But we cannot fold. We have actually studied a little bit the possibility to fold some wings, but they cannot be of this material. And then then you lose this all the performance that this bird has, because there are a lot of toys that have very thin wings that can flap, but no way they can flap in these four wings because it is rigid and it's very fast. It's very stable in some sense. Yeah.
The end of life for this bird and how you manage the power?
Very good question. So of course you can imagine this is one motor that basically connects this mechanism, and there is this magic relation between the heave and the pitch. So there is a certain angle that creates these vortices in order to fly. But for the rest, there is one motor that basically creates this crank mechanism that creates this. And then to steer it, you have, you can in the tail, you have differential tail that you can pitch in a continuous mode, and you can roll if you have differential mode. But if you flap, you can fly it about maximum 15-20 minutes. It uses a lot of power. And in fact, if you see the bird, you cannot recognize the bird, but you can hear it. Because the mechanic, bird doesn't do so that is actually where a lot of energy is lost. So we optimize the mechanism in the past. A lot of work could be done in that still, I think. Any other question? Yes.
Use a bubble one. I think the whole idea was to flow visualization. I'm not.
Yes, but in 3D.
Flow visualization you can get in the big channel using some kind of fluid.
The problem is that you want to have a 3D flow. Okay, and the 3D flow, it means you have a certain volume that you want to see. You want to see. If you have a camera, a high-speed camera, to see very small particle, it needs to have a certain optics. Okay, yeah. And the focus should be such that the depth should be good here and here. So we needed to have particles which were big enough to be seen here and here if the camera was here. So it's really the depth of the focus of the cameras. And in order to do that, the particle needs to be at a certain size. Now, you need to see the flow and to do particle tracking. And eventually, the machine that you see is a machine that has been developed in Delft, and now LabVision sells it for a lot of money, and basically creates bubbles which are soap bubbles, which are with helium. So the buoyancy of the bubbles is such that they do not influence the measurement, but the size is big enough to be seen the volume that we need to measure.
Is it something similar to PIV?
Yeah, so whether it's PIV, particle imaging velocimetry, this PIV, PTV, particle tracking, PTV velocimetry. So in one, you basically look at the vector fields, and in the second one, which is the one we use, you actually trace every single particle along the flow.
And if your wing is airfoil type shape, it's an airfoil.
The wing?
Yeah.
Yes, the wing has a certain shape, and as a camber in the wing, and it's actually manufactured in 2 stages. So the wing it cannot be manufactured in one piece because it has 2 pieces of curvature. So the first part and the second part of the wing. And we bought a machine, for example, which is a laser. Excuse me, is a hot wire cutter for foam that you could actually numerically steer to make this. But then the wing needed to be cut and composed by hands, and could do like robots. Yes, there's a certain profile which you understand, and you have to strengthen also because foam is not strong enough. In certain point, we need to actually put a strengthening line in order to
Last question. The wing is a serrated wing.
Excuse me?
Is it a serrated wing? The wing at the edges.
Yes.
You tend to have vortices at the end, right? Did you do anything to kill the vortices in terms of?
Oh, okay. No, it turns out that it's essential that the wing is rigid, more or less, but it has a twist. So in fact, the reinforcements that you put, which is on the front edge of the wing, okay, and it allows this distortion. No, it's a shape at a certain point. Yes. Yes. But it's what is crucial. I mean, there could be things I think could be changed. Would not have a lot of effect. What it really had a lot of effect, and we tested it, was this twisting. So it turns out that what I show you in CVT, what computational fluid dynamics that I show you before, in 2D